Binary stars sometimes interact by transferring mass. The gravitational fields of the two stars, plus the rotation of the binary system, produce a dumbbell-shaped volume around the pair of stars called the Roch lobes. The surface of this volume is called the Roch surface. The size of the Roch lobes depends on the mass of the stars and on the distance between the stars. The Lagrangian points are places in the orbital plane of a binary star system where a bit of matter can reach stability. The most important of these is the inner Lagrangian point, where the two Roch lobes meet. If matter can leave a star and reach the inner Lagrangian point, it can flow onto the other star. Therefore, the inner Lagrangian point is the connection through which the stars can transfer matter. There are only two ways matter can escape from a star and reach the inner Lagrangian point. Firstly, if a star has a strong stellar wind, some of the gas blowing away from it can pass through the inner Lagrangian point and be captured by the other star. Secondly, if an evolving star expands so far that it fills its Roch lobe, which can occur if the stars are close together and the lobes are small, the matter can overflow through the inner Lagrangian point onto the other star. In some binary systems, the less massive star becomes a giant, while the other more massive star is still in the main sequence. If higher mass stars evolve faster than lower mass stars, how do the lower mass stars in such binary systems manage to leave the main sequence first? This is the Algol paradox. Mass transfer explains how this could happen. Imagine a binary system that contains a 5 solar mass star and a 1 solar mass companion. The two stars form at the same time, so the higher mass star, evolving faster, leaves the main sequence first. When it expands into a giant, however, it fills its Roch lobe and transfers the matter to the low mass companion. The higher mass star loses mass and evolves into a lower mass star, and the companion gains mass and becomes a higher mass star that is still in the main sequence. This explains how there could be a system such as Algol that contains a 5 solar mass main sequence star and a 1 solar mass giant. Mass transfer through the inner Lagrangian point in a binary system toward a star must conserve its angular momentum, or the tendency of a rotating object to continue rotating. If the star is small enough, the mass will form a rapidly rotating whirlpool called an accretion disk. Two important things happen in an accretion disk. Firstly, the gas in the disk goes very hot due to friction and tidal forces. The disk also acts as a brake, shifting angular momentum outward in the disk and allowing the innermost matter to fall into the white dwarf. The interior places of an accretion disk around a white dwarf are violent places. The temperature of the gas can exceed 1,000,000 Kelvin, causing the gas to emit X-rays, and the matter falling inward can produce a violent explosion when enough accumulates on the white dwarf. Nova explosions occur when mass transfers from a normal star through the inner Lagrangian point into an accretion disk around the white dwarf. As the matter loses its angular momentum in the inner accretion disk, it settles onto the surface of the white dwarf and forms a layer of unused nuclear fuel consisting mostly of hydrogen. As the layer deepens, it becomes denser and hotter until the hydrogen fuses in a sudden explosion that blows the surface off of the white dwarf. Although the expanding cloud of debris contains less than 0.0001 solar mass, it is hot, and expanding surface area makes it very luminous. Nova explosions can become 100,000 times more luminous than the sun. As the debris cloud expands, cools, and thins over a period of weeks and months, the nova fades from view. The explosion of this material hardly disturbs the white dwarf and its companion star. Mass transfer quickly resumes, and a new layer of fuel begins to accumulate. One can expect nova to repeat each time an explosive layer accumulates. Many novae take thousands of years to build an explosive layer, but some take only decades. Mathematical models of the sun suggest that it may survive for an additional 5 billion years or so, but it is already growing more luminous as it fuses hydrogen into helium. In a few billion years, it will exhaust the hydrogen in its core and swell into a giant star about 100 times its current size. This giant star will be about as large as the orbit of the Earth. The sun's growing luminosity will evaporate the Earth's oceans, drive away the atmosphere, and even vaporize much of Earth's crust. Models predict that the expanding sun will eventually become large enough to totally engulf Earth. While as a giant star, the sun will lose mass into space, and most of the atoms that were on Earth will be part of the expanding nebula around the sun. If it becomes hot enough, it will ionize the expelled gas and light it up as a planetary nebula. The sun will probably not explode as a nova because, unless Nemesis turns out to be real, it has no binary companion. Nor is the sun big enough to die the violent death of massive stars.